that we have a structure for compound D, let's solve the next part of the synthesis. And here we have compound D and then going to E and F. And as you can see, F has the molecular formula. So let's apply similar counting process to develop an idea on what could happen in these two steps. So as you can see, compound D has 12 carbon atoms. You can see from both molecular formula and from the structure that we have found. And compound F molecular formula, it says that it has 7 carbon atoms. So let's calculate HDI again because we have full molecular formula in order to gain an insight towards the structure of compound F. So yes, again using the same formula, we calculate the maximum number of hydrogens and the hydrogen deficiency index of 2, and it could imply again one of these things. Now having HDI calculated, let's see how it can help us. So since we are using a base on D ester here, followed by decarboxylation conditions, we can propose a Claisen condensation here. And HDI of F helps us a lot here, since we know that we should have 2 elements of unsaturation. Indeed, intermolecular Claisen condensation will yield a ring. So we would have a ring because we are just applying a base to D ester. So this would cyclize and we would have a ring here from the Claisen condensation and a ketone double bond. So having one ring and one pi bond would yield of HDI equal to 2, which is in a perfect alignment with our calculation. So let's see the mechanism and the structure of E as we propose a Claisen condensation here. So what's going to happen is a base, sodium ethoxide, is going to deprotonate. So we have actually 2 sides, but there's no any hydrogen here. So it's going to deprotonate here. It will attack nucleophilic acyl substitution, will go up, carbonyl group will reform, and then ethoxide will leave. We will have this compound, and actually compound E is this one. So most people here are confused and they might show this as the final structure for E. But as you can see, there is no, as you go in the previous slide, there is no any quench step, there's no any workup step, there's no any water, there's no any proton source. So this compound E is actually this one, because Claisen condensation goes all the way to deprotonation. Actually, this step is very important here because this is what drives the whole Claisen condensation reaction. This should be the compound structure of compound E. And now we got our compound E, which is subject to decarboxylation. And we show mechanism in the next slide for this decarboxylation. So we have compound E and we have potassium hydroxide in the first step, which is going to hydrolyze. So it's going to be like a base catalyzed hydrolysis of ester. And we are going to form again this compound because since we are using a basic condition, we cannot have OH here. It's going to be O minus. So we have like the anion here. And then it's going to be protonated in the second step. We will have CO and this will be protonated and this will be like carboxylate anion, become carboxylic acid. And then with a bit of temperature here, we are going to lose carbon dioxide and we will form an enol, which is going to be tautomerized back to ketone. So here I forgot to put 2 methyl groups. So sorry for that. And now we have the structure of compound E, which is going to be a sodium salt. You can show it like this, a negatively charged anion coupled with a counter ion, which is sodium plus here because we are using a base with a sodium. And then the structure of F is going to be this, a ketone. It has indeed 7 carbon atoms and 2 HDI, 1 ring and 1 double bond and just 1 oxygen. And this is going to be really easy. It's a reduction. So if you remember the first slide, we said we are expecting a ketone or aldehyde for F. And we are expecting G to be an alcohol. So indeed, this is what happens. And we get our secondary alcohol. So let us zoom out and see the overall synthesis again. And we found all the way until G. And let us focus on the last part of the synthesis from G to compound 3. So we have the structure of G as a secondary alcohol. We already know that. And what's going to happen in case this is anhydride and this is alcohol? So what's going to happen is we are going to convert hydroxyl group into a better leaving group, an ester, so that in upcoming reactions it can leave better because hydroxyl group itself is really bad leaving group. And as you can see here, we have high temperatures, which suggest a possibility of elimination. And this would yield us compound with a double bond. And obviously what could happen here is that we can use water maybe in the system. And this could deprotonate like this. So we have a base. It could go here and it can go like this. So we will have a double bond here and that could be the compound J. And this is embromosuccinimide as I introduced in the first slide. it's a brominating agent. And what's going to happen is a radical bromination at allylic position. Because this is radical bromination, right? So we are going to start with a proton abstraction. And a proton is going to be abstracted from the weakest CH bond. And what is the weakest CH bond here? Obviously this bond. Why? Because when we break this bond homolytically, we are getting a radical at this point, and this is very stable radical. So radical stability is inversely proportional to the bond strength. The more stable the resulting radical is, weaker the H bond is gonna be. So now, actually, this is quite easy because now we have a base. Pyridine functions as a base. So it's gonna be a similar reaction from H to J, elimination reaction, and you will get this compound. And as you can see, this is quite symmetric compound. This is not guaranteed to be 100% sure every single time, but when you have this kind of synthesis, you usually end up with a nicely looking structures, like something symmetrical, something extraordinarily beautiful structure. So this is actually quite symmetrical, and that actually also confirms our whole synthesis, that we did all the synthesis to get this nice symmetrical molecule. And now we can put this back to this initial slide that I showed you. So compound 3 is this one.